In this lesson, we're going to look at how a Nexus switch operates. Cisco's NXOS software provides isolation between control plane functionality and data plane forwarding within the device. This isolation is very important, and it means that a disruption within one area, such as the control plane or the data plane, does not disrupt the other. To understand this better, let's take a look at a Nexus 5000 series switch. The hardware in this switch is based on two custom ASICs. It's based on a set of unified port controllers called UPCs that perform data plane processing and a unified crossbar fabric ASIC that cross-connects the UPCs together. The UPC ASIC manages all the packet processing operations on ingress and egress interfaces. The UPCs provide distributed packet forwarding capabilities. 4 switch ports are managed by each UPC, and a single UCF ASIC interconnects all of the UPCs. The UCF schedules and switches packets from the ingress to the egress UPCs and is simply known as the fabric. All port-to-port traffic passes through the unified crossbar fabric. The Nexus 5000 control plane is responsible for managing all of the control traffic. The data frames actually bypass the control plane and are managed by the ASICs that we just discussed. Things like BPDUs and fabric login frames and other control-related frames are managed by the control plane supervisor. The control plane is also responsible for running the Cisco NXOS software. So you can see why it's very important to keep the control plane up and running. In regards to the IP routing and forwarding, NXOS and Nexus switches strongly decouple that control plane and the data plane. The routing and forwarding tables are built on the control plane using routing protocols or static configuration. Some of these routing protocols are OSPF, EIGRP, and BGP, which we use for dynamic routing. Once these tables are built, they are then downloaded to the forwarding engine hardware for data plane forwarding. In regards to IP multicast routing and forwarding, the forwarding tables are once again built on the control plane using multicast protocols, such as PIM sparse mode, or MSDP. Once the tables are built, it is similar to what we discussed before. The tables are downloaded to the forwarding engine and the replication engines for data plane forwarding. So not only is it important for high availability and redundancy to separate our control plane traffic and our data plane traffic, but this also lends itself to a very high performance switch because the data plane is distributed and decisions can be made very quickly in hardware. This type of architecture is deployed on all of the Nexus devices. Please join me for the next lesson, examining Nexus virtualization features.